We're going to look at two of the more recent differential equations for your responses and try to find what kind of things that happen consistently. The first thing we should notice is that we have a differential equation. We have what the slope is at different x and y values. And in this problem, they give us a slope field. This comes up sometimes, but not on every problem. And it says to sketch the solution curve that passes through the point 0, 2. And the solution curve that goes through the point 1, 0. So it's given us these points, and in general, we're just going to follow the slopes because the solution curve that goes through that point also needs to have the slopes as shown. And so this is the solution curve at y equals 2. And the solution curve at y equals 1 is a little harder. Looks like goes something like this, you know, and down here it looks like it's bending and then going up and then bending like that, something like this. In order to get these points, you just needed to follow the slopes. Did yours have to look exactly like mine? No, of course not. Well, on the top one it did, but on the bottom one it could have been a little bit different and it would have been okay. But these, in general, you're just going through the point it tells you and following the slopes as they look on the graph. The second one, this is super common. Unlike the differential, this one comes up about 1 out of every 3 years. This one comes up most years. It gives you, it says y equals f of x is the particular solution to the differential equation, which means it's the actual function that has these slopes. And it wants us to use the point 1, 0 and write an equation for the tangent line. So when we have an equation for the tangent line, we need a slope and we need a point, and we're going to use it to approximate f of 0.07. So the first thing to do is to write the equation of the tangent line. And we want to say, I'm going to put b here. We want to say dy dx. We want to label that we found our slope at the point 1, 0. And here we're just going to use this equation. When x is 1 and y is 0, we're going to find that the slope is 4/3. And so the equation is y equals 4/3 x. And then the y value there was 0. We don't need to put plus 0, obviously. It's fine to just put y equals 4/3 x. Hold on. Something seems wrong here. Sorry, this is not right, JK. Y equals 4/3 x minus 1 plus 0. Great, that's better. And then it says to use it to approximate f of 0.7. So f of 0.7 is approximately equal to, if you use the equal sign there instead, you won't lose the point, but you should put the right thing. So 4/3 times 0.7 minus 1. And you can stop right here. This will get you full credit. If you feel like you need to simplify, you know, this is negative 0.3, and then the multiplying by 3 and dividing by 3, but then you have a 0.1 there, so it's negative 0.4. I mean, I see some kids mess this up sometimes. I would much prefer you to just stop where you'll get full credit and be guaranteed the points. Okay, and part C is the crucial part. This is the part that is in every year's differential equations, almost without fail. I guess there's been a couple without it, but almost every time it's there. It wants you to find the particular solution. The key word here is it wants you to get the actual solution to the equation with the initial condition. Okay, so here's where we're going to start with dy dx equals 1/3 x times y minus 2 squared. We do not need to rewrite it, but if you want to, you could. And the first point that's always given out is for separating variables. The dx is going to get multiplied on both sides. So the dx will be over here. And that means the x's will always have to be on the right side. And the y's will always have to be on the left side. So almost always you'll be dividing by y minus 2 squared, although sometimes it could be multiplying. So when we divide by y minus 2 squared, we get dy over y minus 2 squared equals 1/3 x dx. And we've separated the variables. It's also completely fine to put this as 1 over y minus 2 squared dy equals 1/3 x dx. And the only thing that makes these problems different from year to year is that the function we're going to need to integrate changes. We're going to do the integral of both sides. And here, this is clearly a chain rule thing. This is a u substitution. U is y minus 2. Luckily, du is just 1, so it's not even going to matter that it's a u substitution. This is 1 over u squared, which is u to the negative 2 power. So when we do the integral of u to the negative 2 power, this is going to be negative u to the negative 1 power. And I'm going to rewrite that up there with, I'm just going to substitute back in. This is going to be negative 1 over y minus 2. That's what our u was. That's it to the negative first power. And that's going to equal, here we need to use the power rule and divide by 2. And we need to put a plus c. We could have put a plus c on this side as well, but it's completely unnecessary because the two constants, when you move them together, will combine into a single constant. The next step is always to solve for y. We could stop and get c right now, or we could solve for y. It doesn't really matter. If you've got a y in the denominator, this step will be different from problem to problem, year to year. In this case, I would multiply by y minus 2 to get it out of the denominator, and then divide by what the y minus 2 is being multiplied by. So y minus 2 equals negative 1 over 1/6 x squared plus c. And so y equals negative 1 over 1/6 x squared plus c plus 2. And the last step is to plug in for c, or to plug in to find c. And we've got this initial condition that we're going to need to use, 1, 0. And so I'm going to plug in when x is 1, y is 0. So let's see. I guess I could plug in here, but it looks like it's going to be kind of annoying because I'll have to resolve for c. I'm going to go back to here because this seems like a good place to solve for c. I'm going to plug in y is 0 and x is 1. So negative 1 over negative 2. 0 minus 2 is negative 2, equals 1/6 times 1 squared is just 1/6 plus c. So I'm comfortable saying a negative divided by a negative is a positive. And it's fine to just leave this like this if you want and plug it in. If you feel good about your fraction skills, you can obviously say c is 1/3. So let's see, this is negative 1 over 1/6 x squared plus 1/3. That's plus 2. That's what y is. And that's our final answer for the solution to the differential equation. Let's do one more and see how it could be a little bit different. This was from the year before. And this one, the math was just as easy, but the wording was a little bit tricky on it. It told us at time equals 0, a boiled potato is taken from a pot and it starts cooling. It gives us the initial temperature of the potato. So we've got this 0, 91 degrees. And it tells us it's always greater than 27 degrees. Okay. The differential equation is given by this. And the first thing it asks us for is to write an equation for the tangent line. So we saw that last time. We need a point and a slope. And so we need dh dt at 0, 91. So h is the temperature. And so it's going to be negative 1/4 times 91 minus 27, which is negative 1/4 times, this is a place where you don't want to mess up, but you might. It's negative 16. Again, if you don't feel comfortable doing that, you can leave the slope as this. Okay, and then I'm going to finish writing a down here. This should really go here. Then we're going to get y equals the slope times t, because this is about t, minus 0 plus 91, or negative 16t plus 91. Okay. And it asks us to approximate the internal temperature at time equals 3, and so we'll call it h of 3 is approximately equal to negative 16 times 3 plus 91. Again, you will get full credit if you stop right there. If you feel like simplifying, you can, although this makes it more likely that you make a mistake. Okay, B. Sometimes it asks us, this is a new question, it asks us to find the second derivative. So here we're finding d squared h dt squared, and so we're doing the derivative of the derivative with respect to t. The one thing to be careful with here is that this is a constant multiplier times the derivative of the inside. Remember, we're doing it with respect to t, and so the derivative of h is not 1. H is our y here, and so we get dh dt minus 0. And it asks us always to do it with respect, usually we want it simplified, and we want to plug back in what dHdt is. So it's negative 1/4 of negative 1/4 h minus 27, which is 1/16 h minus 27. Again, if we stopped here, this would be good enough. And it asks, is it an overestimate or an underestimate? Well, this is where we have to use concavity. The second derivative tells us concavity, and because we know that the temperature is always above 27, the second derivative will always be positive. So dH dt is greater than 0 because h is greater than 27. So our estimate was if the function is concave up, our tangent line is an underestimate. C will again be the solving, but it gives us a new model. It now says dg dt equals this guy. dg dt equals negative g minus 27 to the 2/3 power. And I'm going to get again, we're always going to multiply here, separate our variables. dg equals negative. Now this is g. It needs to go with the dg. And so we're going to end up with negative 1 dt, and this is over g minus 27 to the 2/3 power. We're going to need to take this integral, and one thing to note is that this is a power rule thing with a u substitution, just like before. This is going to be u to the negative 2/3 power du, and the derivative of u is just 1. Here, this is going to be t plus c. Make sure, because it's dt, we don't put plus x. I'm going to stop there and leave it to you to practice doing some integration.